Learning to rank or machine-learned ranking is the application of machine learning, typically supervised, semi-supervised or reinforcement learning, in the construction of ranking models for information retrieval systems. Training data consists of lists of items with some partial order specified between items in each list. This order is typically induced by giving a numerical or ordinal score or a binary judgment for each item. The ranking model's purpose is to rank, that is, produce a permutation of items in new, unseen lists in a way which is similar to rankings in the training data in some sense. Learning to rank is a relatively new research area which has emerged in the past decade. Applications: in information retrieval. Ranking is a central part of many information retrieval problems, such as document retrieval, collaborative filtering, sentiment analysis, computational advertising. A possible architecture of a machine-learned search engine is shown in the figure to the right. Training data consists of queries in documents matching them together with relevance degree of each match. It may be prepared manually by human assessors, who check results for some queries and determine relevance of each result. It is not feasible to check relevance of all documents, and so typically a technique called pooling is used. Only the top few documents, retrieved by some existing ranking models, are checked. Alternatively, training data may be derived automatically by analyzing click-through logs, query chains, or such search engines features as Google's Search Wiki. Training data is used by a learning algorithm to produce a ranking model which computes relevance of documents for actual queries. Typically, users expect a search query to complete in a short time, which makes it impossible to evaluate a complex ranking model on each document in the corpus, and so a two-phase scheme is used. First, a small number of potentially relevant documents are identified using simpler retrieval models which permit fast query evaluation, such as vector space model, Boolean model, weighted and BM25. This phase is called top document retrieval, and many good heuristics were proposed in the literature to accelerate it, such as using document static quality score on tiered indexes. In the second phase, a more accurate but computationally expensive machine-learned model is used to re-rank these documents. In other areas, learning to rank algorithms have been applied in areas other than information retrieval, in machine translation for ranking a set of hypothesized translations. In computational biology for ranking candidate 3D structures in protein structure prediction problem. In proteomics for the identification of frequent top-scoring peptides. In recommender systems for identifying a ranked list of related news articles to recommend to a user after he or she has read a current news article. Feature vectors, for convenience of MLR algorithms, query document pairs are usually represented by numerical vectors, which are called feature vectors. Such approach is sometimes called bag of features and is analogous to bag of words and vector space model used in information retrieval for representation of documents. Components of such vectors are called features, factors or ranking signals. They may be divided into three groups: query-independent or static features are those features, which depend only on the document, but not on the query. For example, page rank or document's length. Such features can be pre-computed in offline mode during indexing. They may be used to compute documents' static quality score, which is often used to speed up search query evaluation. Query-dependent or dynamic features are those features, which depend both on the contents of the document and the query, such as TF-IDF score or other non-machine-learned ranking functions. Query-level features or query features, which depend only on the query. For example, the number of words in a query. Further information, query-level feature, some examples of features, which were used in the well-known LETOA dataset, TF, TF-IDF, BM25, and language modeling scores of document zones for a given query. Lengths and IDF sums of document zones. Documents page rank, its ranks and their variants. Selecting and designing good features is an important area in machine learning, which is called feature engineering. Evaluation measures, There are several measures which are commonly used to judge how well an algorithm is doing on training data and to compare performance of different MLR algorithms. Often a learning-to-rank problem is reformulated as an optimization problem with respect to one of these metrics. Examples of ranking quality measures: mean average precision, DCG and NDCG. Precision at n, NDCG at n, where at n denotes that the metrics are evaluated only on top-n documents. Mean reciprocal rank. Kendall's tau, Spearman's rho, DCG and its normalized variant NDCG are usually preferred in academic research when multiple levels of relevance are used. Other metrics such as MAP, MRR and precision, are defined only for binary judgments. Recently, there have been proposed several new evaluation metrics which claim to model users' satisfaction with search results better than the DCG metric, expected reciprocal rank. Yandex is found. Both of these metrics are based on the assumption that the user is more likely to stop looking at search results after examining a more relevant document, than after a less relevant document. Approaches. Tai-Yan Yu of Microsoft Research Asia in his paper Learning to Rank for Information Retrieval, and talks at several leading conferences has analyzed existing algorithms for learning to rank problems and categorized them into three groups by their input representation and loss function. Pointwise approach. In this case it is assumed that each query document pair in the training data has a numerical or ordinal score. Then learning to rank problem can be approximated by a regression problem given a single query document pair, predict its score. A number of existing supervised machine learning algorithms can be readily used for this purpose. Ordinal regression and classification algorithms can also be used in pointwise approach when they are used to predict score of a single query document pair, and it takes a small, finite number of values. Pairwise approach. In this case learning to rank problem is approximated by a classification problem learning a binary classifier that can tell which document is better in a given pair of documents. The goal is to minimize average number of inversions in ranking. Listwise approach. These algorithms try to directly optimize the value of one of the above evaluation measures, averaged over all queries in the training data. This is difficult because most evaluation measures are not continuous functions with respect to ranking models' parameters, and so continuous approximations or bounds on evaluation measures have to be used. List of methods. A partial list of published learning to rank algorithms is shown below with years of first publication of each method. Note, as most supervised learning algorithms can be applied to pointwise case, only those methods which are specifically designed with ranking in mind are shown above. History. Norbert Fuhr introduced the general idea of MLR in 1992, describing learning approaches in information retrieval as a generalization of parameter estimation. A specific variant of this approach had been published by him 3 years earlier. Bill Cooper proposed logistic regression for the same purpose in 1992 and used it with his Berkeley research group to train a successful ranking function for TREC. Manning et al. Suggest that these early works achieved limited results in their time due to little available training data and poor machine learning techniques. Several conferences, such as NIPS, SIGIR and ICML had workshops devoted to the learning to rank problems since mid-2000s. Practical usage by search engines. Commercial web search engines began using machine-learned ranking systems since the 2000s. One of the first search engines to start using it was Alta Vista, which launched a gradient boosting trained ranking function in April 2003. Bing's search is said to be powered by RankNet algorithm, which was invented at Microsoft Research in 2005. In November 2009 a Russian search engine Yandex announced that it had significantly increased its search quality due to deployment of a new proprietary matrix net algorithm, a variant of gradient boosting method which uses oblivious decision trees. Recently they have also sponsored a machine-learned ranking competition Internet Mathematics 2009 based on their own search engine's production data. Yahoo has announced a similar competition in 2010. As of 2008, Google's Peter Norvig denied that their search engine exclusively relies on machine-learned ranking. QL's CEO, Tom Costello, suggests that they prefer hand-built models because they can outperform machine-learned models when measured against metrics like click-through rate or time on landing page, which is because machine-learned models learn what people say they like, not what people actually like. References. External links, competitions and public data sets, LETOR, a benchmark collection for research on learning to rank for information retrieval, Yandex's Internet Mathematics 2009, Yahoo! Learning to Rank Challenge, Microsoft Learning to Rank Datasets, Open Source Code, Parallel C++/MPI Implementation of Gradient-Boosted Regression Trees for Ranking, released September 2011, C++ Implementation of Gradient-Boosted Regression Trees and Random Forest for Ranking, C++ and Python Tools for Using the SVM Rank Algorithm,